linear models. Previously, we've been discussing statistical inference procedures. We were looking at scenarios where we were comparing different populations, and we said that we want to draw inferences of these populations by observing different samples and building up a statistical model of the properties of those samples. So now we'll talk about the class of models known as linear models. They are just used for this purpose of trying to build up models of samples. It doesn't necessarily have to restrict itself to just this simple scenario here where we did health versus disease individuals, but we could as well think about properties of individual samples where we want to make models such as regressions models, or maybe we have more than two-way comparisons, like we want to compare 3 different patient groups. So we build up a statistical model and we look if does this model explain more of the variance in the data than you just expect by chance. So typically we build up a null model where we say that they do not explain more than what you would expect by chance, and then we try to refute that. So a typical scenario where we look at, we have sort of collected a sample where we are having one variable x that's sort of dependent, or the measurement variable y is a dependent of the input variable x. So we could try to build up a statistical model of this. For instance, we could say that we have a model f of x that's just directly proportional to the input variable x with an offset of an intercept b. We can sort of examining how well this model now fits to our data by calculating what we know as the residuals, or E in this example. So E just is the difference now between the observed variable, y, and the outcome of the model. So we can sort of, from the data itself, we can fit the model by selecting A and B in such a way that they minimize the squared sum of the residuals, that is the E's now in square. And this will give us a perfect fit, something like, or as good enough fit as possible, much like the line here that we have drawn to the diagram to the left. And the key here is now that we can use statistical testing, or in this case an F-test, to see if these residuals are larger enough than expected, or that is at least true as long as your residuals are normally distributed, or Gaussianly distributed if you want to prefer that. So by just evaluating this and using some kind of statistical package is often most used, but you can as well, of course, do this manually by hand. I won't go through the calculations themselves because they're quite intricate, but it's obvious actually to understand that what these packages do for you is just trying to fit a regression line, or trying to fit a statistical model to your data and see, does this explain more of the variance than you expected by chance. Actually, there's maybe the same type of thinking could actually be applied just straight out of the box, exactly the same way for categorical variables as well. Say that we, instead of having a regression of a regular function, we instead make this regression as a function of a variable x that's discrete in its function. This could be a dummy variable. This is often called a dummy variable because your categorical variables are often named something like disease and healthy. So here, say that we want to compare the disease individuals that are maybe marked with a 0 and to the healthy one with a 1. We can do exactly the same type of regression as we just did. Actually, and the statistical model would in this case be exactly the same way as we did before. Namely, we can just put it as AX plus B. Just as before, we have a set of residuals, EI, which is the difference between the observed variable and expected outcome. And now you can sort of just as before, you can fit this model to get the A and B that minimize the squared sum of the residuals. And we can investigate if this sort of lowers the squared sum of residuals more than expected by chance. Okay, actually in reality, maybe you would not do it exactly this way, because you probably put a model that sort of works out of means rather than because you could sort of easily calculate the mean of all the variables with 0 and all the ones with 1s. However, this is what we sort of for the sake of the exercise here, or for the sake of the lecture, we can treat this as just the same setting. So what I want to prove for you, or what I want to do here, is just to show you that these two scenarios where you have categorical variables or a linear input variable, they're sort of they look very similar to a model. This later scenario here, where we are testing case and control, that's when we evaluate that with a linear model, we often call this an ANOVA. But actually, for the case here where we only have one variable and that we're testing, this would be also known as a t-test, or at least it would be equivalent to a t-test, or a student's t-test, that is. Okay, so the way we express these kind of functions, so you remember I made a f of x, that was axb, ax plus b. The way we express these relationships is there's this sign language for doing it inside of much of statistical testing, where we set the variable that we want as an output variable, y. We put it as a function of the input variable x. Sometimes you see the notion that they call the x here as the independent variable and y the dependent variable. And this has to do with that y is a function of x, and hence it's sort of it's dependent on the input of x, and that's what we want to test. Let's move over to a more complex scenario than the ones I've showed you so far, and your Jupyter notebook contains, the GitHub page of this contains an example from breast cancer. It's a gene known as the KNAP2 gene, and it's sort of known to be related to the outcome of patients with breast cancer. So here somebody has sort of monitored a set of variables for patients or for cancers with for different breast cancers. And they have noted what grade of cancer it is, which node it is, and what size of the tumor you got, what age of the patient it got, etc. and as well they are displaying the expression of the KNAP2 gene. So done so for 23 different patients, and now the question is, do we see any sort of relationships between the variables, the different variables here? Do we see if there's any relationship between the gene expression and the fact that you have which grade of the tumor you got, and if whether you removed or not removed your lymph nodes? So here they have given variables for us already, where you say that if the node is set to 0, it means that the lymph nodes are still intact, or if it's 1, they have removed the lymph nodes. And if we just start by plotting these the gene expression here, or rather the log gene expression, as a function of what grade and what node you have of your cancers, you will note that actually there's a much lower expression inside of grade 1 tumors than in grade 3 tumors. Furthermore, there seems to be an inverse relationship between being having a high grade and being between the node and the grade. So there seems to be an interaction going on between the nodes and the grade of the tumor. Okay, so we can put up different types of tests for this, and here I'll show you one test here, and that's just putting up the logged gene expression as a function of the grade plus the expression of the average node expression, and as well an interaction term between the grade and the node. So this is a sort of a little bit more advanced function than the one we showed before. There's good packages inside of Python that can help you this sort of executing such a model. In this case, it's called stats models. R got a similar package, or a more famous package known as LM. Okay, so the outcome of such a model could be printed, and here we see now the observed variables, or the input variables, and as well they're associated with their F statistics, and furthermore a P value towards the end here. That's sort of an indication of how much we refute the null model, that these does not have any effect on the outcome. So it seems like there's a very low p-value here for the grade of the so there's the model says that there's with a very high likelihood, or very high probability, very low probability, the null model, that there's no effect what the grade could be, and that's sort of saying that, well, it's quite obvious when you look on the data that there's much more expression in the grade 3 tumors than in the grade 1 tumors. Okay, there seems to be some support as well for that the fact that the nodes are different. So if you have your nodes, it seems like you have a higher expression as well of the gene. But as you can see, this is not necessarily true for the higher grade tumors. So if you test on the interaction terms between the grade and the node, you will find a much lower p-value. That's a p-value of 10 to the, or of 7 per milli, which is sort of normally seen as statistically sound, or like a strong support for the hypothesis. So seeing that this interaction term here between the grade and the node means that we see that, okay, so it's not just that the grade itself affects the tumor, but as well there's interaction between this and if you did or did not remove your lymph nodes. Okay, so actually at this point I should of course mention as well that this doesn't say anything about the causality of this. It just looks at the model itself, at the data itself. It doesn't say that if you remove your lymph nodes you will get a higher expression. It rather says that maybe that the physicians in this case, or the surgeons in this case, chose to remove the lymph nodes when the tumor seemed grave. Okay, let's step this up one step further and we start to look on yet another variable. Let's see if the size of the tumor has any effect on the tumors. So here I started a plot now as well, not just the gene expression as a function of the nodes and whether we remove the nodes and the grade of the tumor, but as well included the size here in this plot. As you can see now, there seem to be a little bit different stories going on for the different grades of the tumor, and that there seems to be a different type of correlation between the data. Again, this is from very low number of data points, so maybe we shouldn't trust this too much. But still, we could do the testing here and just in order to check. So if we now sort of evaluate the model where we include both the grade of the tumor, the node size, and well, we introduced a linear variable of size as well to this. Do we get a good fit? Actually, the model now reports a p-value of 0.9 for the size having an effect into this model, which might be reasonable due to the low sample size. But maybe there's a sort of a link now between the grade of the tumor as well as the to the size as well, and that is, can we see that there's interaction going on between the tumor grade and the size of the tumor? And it seems like we got a much lower p-value here for the link between size and the grade. It's 0.01, which is often considered as a statistically like really measuring a true effect. So we can say that actually it seems like although there's no real interaction or there's no direct link between size of the tumor and the log and the gene expression, we can sort of see that there's sort of when we take the grade in account as well, we can see that there's sort of interaction going on between the grade and the size of the tumor.